In this lesson, we're going to introduce the basics of organometallics, focusing on organolithium and organomagnesium reagents. Organometallic chemistry is easily one of the most important and heavily studied subdisciplines in the field of organic chemistry. An organometallic is simply a compound that has a carbon-metal bond. You may have already seen acetylide ions, which are organometallic reagents prepared from terminal alkynes. As you can see in the examples, the carbon-metal bond of an organometallic reagent can be drawn as either a covalent or ionic bond. In reality, most carbon-metal bonds fall somewhere between those two extremes. It's important to recognize that not all organic molecules that possess a metal are organometallic reagents. This example shows an alkoxide, and as you can see, the metal is bonded to oxygen, not carbon, so this is not an organometallic. Organometallic reagents are often categorized based on the type of metal in the structure. Classical organometallics have a carbon bonded to a common alkali metal, such as lithium or magnesium. Transition metal organometallics, not surprisingly, have a carbon bonded to a transition metal, such as copper or zinc. The two most important types of classical organometallics are organolithiums and organomagnesiums, usually referred to as Grignard reagents. Organolithiums have a carbon-lithium bond, and structurally have an alkyl or other organic group directly attached to the lithium. Organomagnesiums, or Grignard reagents, have a carbon-magnesium bond. Because magnesium is divalent, Grignard reagents have a magnesium bonded to both an alkyl group and a halide. Both types of classical organometallic are typically prepared by treating an alkyl halide with the appropriate metal. As you can see from the first example, the preparation of organolithiums require 2 equivalents of lithium per equivalent of alkyl halide. 1 equivalent of a lithium salt is formed as a byproduct. Remember that organic chemists rarely balance equations. This second example is a more typical representation for the preparation of an organolithium. Grignard reagents are prepared by treating an alkyl halide with 1 equivalent of magnesium metal. The second example is a more typical representation for the preparation of a Grignard reagent. Most of the functional groups you'll encounter when studying organic chemistry involve carbon bonded to an electronegative element, such as a halogen or oxygen. This places an electron deficiency on the carbon, making the carbon electrophilic. In contrast, most metals are less electronegative than carbon. This means that the carbon-metal bond found in an organometallic reagent places extra electron density onto the carbon, making it electron-rich. The increased electron density on carbon makes classical organometallic reagents very powerful carbon nucleophiles. Classical organometallic reagents are therefore very useful for making carbon-carbon bonds. So here we see 2 common and very useful examples. The first is the alkylation of an alkyl halide, typically with an organolithium or, less frequently, with a Grignard reagent. In this example, ethyl lithium reacts with 1-bromopropane to form pentane, and results in the formation of a new carbon-carbon bond. You can see that the mechanism is a simple SN2 reaction. The electron-rich carbon of the organolithium reagent acts as a nucleophile and attacks the electron-deficient carbon of the alkyl halide, displacing the halogen as a leaving group. A similar reaction is the alkylation of an epoxide with an organolithium or Grignard reagent. You might recall that epoxides undergo ring opening reactions via nucleophilic attack onto one of the 2 electrophilic carbons of the ring. Treatment of an epoxide with an organolithium or Grignard reagent results in the formation of a carbon-carbon bond and an alcohol. Note that regioselectivity must be considered when reacting epoxides that are differentially substituted. You might remember that nucleophiles attack epoxides at the less substituted carbon of the ring under non-acidic conditions. In this example, the organometallic reagent attacks the less substituted carbon on the right side of the ring, resulting in the formation of an alcohol on the left side. Don't let the presence of an acid in that second workup step throw you off. The acid is introduced only after the nucleophilic attack occurs, which means the reaction occurs under non-acidic conditions. The reaction mechanism is pretty straightforward. In the first step, the nucleophilic organometallic reagent attacks an electrophilic carbon on the epoxide, forming a carbon-carbon bond and displacing the bond to oxygen. In the second step, an acid is introduced to protonate the alkoxide formed from the first step, resulting in the formation of an alcohol. The acid must be introduced after the nucleophilic organometallic reagent has attacked the epoxide. Because classical organometallic reagents are powerful nucleophiles, this means that they're also powerful bases. Organolithiums and Grignard reagents are completely incompatible with protic species. Even relatively weak acids like water will quickly react with these classical organometallic reagents, rapidly protonating them and preventing them from any nucleophilic attack. One of the challenges in working with these reagents is that the reactions must be performed under completely anhydrous conditions. Even the smallest amount of moisture can prevent the intended reaction from occurring.